Okay, in this video we're going to pick up where we left off, and we'll continue to talk about our shell method for integration. Now before we get to the problem that's it's going to be similar to what you'll see on the test, let me just remind you that the goal with the shell method is to create these concentric cylinders, if you will, when we revolve an object. So this object's going to have a cylinder area, if we're worrying about the lateral area, and then we'll have another one that surrounds it, and then another that surrounds it, and so on. So the notion here is that we're concerning ourselves with the lateral area of each of these cylinders, and the lateral area is 2 pi times the cylinder's radius times its height. Now the radius is relatively easy to obtain. The radius of any one of these shells is the measurement from the axis of revolution to that position along that axis. So in this case, when revolving around the y-axis, we would end up generating a radius based on the x-coordinate. The height, on the other hand, is the height of each of the cylinders that's being generated. And so the height is the difference between the upper and lower function. So when we concern ourselves with the shell method, again, we're worrying about the cross-sectional area of these concentric cylinders. Now this diagram was taken from a problem that asked for a rotation or revolution around the x-axis using a different method. So that's why we're not going to talk so much about it right now. Instead, let's focus on number 7 here. We're being asked to use the shell method to find the volume when revolved around the x-axis. So here we are revolving around the x-axis, and if we're having trouble using the shell method to revolve around the x-axis, then you could also complete this using the disc or washer method, revolve around the x-axis. Either of these techniques, since we're talking about the same 3D object, should produce the same volume. Now let's talk about the shell method for just a second, the volume based on shells. Again, we're talking about concentric shells. So these are the sides or edges of these shells, if you will, and each of these shell edges produce a concentric cylinder. So we're worried about these cross-sectional areas of these cylinders as they're rotating around the x-axis. So for that reason, we want an integral with respect to y, because we're using the y variable here. And the area for each shell is 2 pi times the radius times the effective height of these shells. Now the radius, again, is measuring from the axis of revolution to the edge of each of these shells. So that's pretty easy to establish. The radius is just whatever the y-coordinate ends up being. Now the height of these shells, and this problem's kind of interesting. The height is measured from this vertical line to this edge. So if I were to use, say, this shell right here, well, that height is basically 49, maybe just a little bit less. This one's a little bit less than 49 and a little bit less, and so on. This one's 49 minus quite a large distance. Now the distance that we're subtracting ends up being the computed result for this region here where the dotted lines are, and those are described by this position, this curve. Now I've got an equation, y equals square root of x, but I don't want my equation to be built on a variable x. I want my equation to be built on variable y. So I'm going to end up calling this x equals y squared. So one more time, while this letter y represents the radius of the cylinder, this computation here represents the height. The height of each one of these cylinders is simply going to be this position, which happens to be a constant 49, that height, 49, minus whatever the y-coordinate is associated with each of these positions. And so the the y-coordinate, but the position based on the y-coordinate, let's say it that way, y squared. So again, since we're revolving around the x-axis, our formula has to be written based on the y variable. That's customary for a shell revolve around the x-axis, but we also need to provide boundaries in the y direction as well. Now this boundary here on the y-axis, of course, starts at 0 but ends at this position, and this position again needs to be computed if 49 is the boundary on the x-axis, and the y value would be the result of the square root of 49, so we'll call that 7. So this should compute a result for me. Now, if interpreting the shell method in this particular case was a bit confusing, I can understand why, because I don't think it's the best method used to find the volume of this particular shape. If I were to take this portion of a parabola and revolve it around the x-axis, I kind of think the washer method or disk method would actually be more appropriate. And if I'm revolving a disk method around the x-axis, it should be relative to x. And our boundaries are x boundaries, so from 0 to 49. And the area is quite simply pi times radius squared. Now, the radius of each of these cross sections is the result of our function, which is already written in terms of x. And we've got the square root of x. And what makes this particular problem even easier is that the square root of x squared is just x. And we've got pi x dx. Computing that volume should be very straightforward. And when I jump over to my calculator, we can see the first integral written with respect to y and the second integral with respect to x both generate the same solution, 2401 pi divided by 2. And again, we do expect both of these answers to be the same because we are generating the exact same object with the same volume using two different methods. Unlike a prior example where we used two different methods, those two methods produced two different objects, and it was okay that the results were different. Let's not forget, I failed to mention in the last video that I will be interested in not only the exact answer off of the calculator, but the approximate answer as well. So be sure to include that when we complete the exam next week. Now, one of the reasons why we like using the shell method is in a scenario like this, we're being asked to find the volume associated with this function when revolved around the y-axis. And at first glance, you might be thinking, well, the washer method should be able to handle this. We just need the outer radius to subtract the inner radius. And to a point, I would agree. However, we only have one function that's describing this curve, and we would end up having to use that function to represent the outer radius and the inner radius, and that makes things a fair bit more complicated. So if we were to use the shell method for this particular case, I like the integral revolved around the y-axis, so we're going to use an integral based on variable x. The boundaries of integration will be 0 to 13. We want 2 pi times the radius, which is x in this case. The radius of each of these shells is the distance from the axis of revolution, times the height. Now the height in this case is just the top end of this function, so 13x minus x squared, and that computation gives us our volume, which is 28,561 pi divided by 6.